So if we are using specific heat capacity to find temperature change, that means we're solving for delta T. But don't forget that delta T is the difference in temperature. So that is the final temperature minus the initial temperature. So also feasibly, you could be asked to solve for either the final temperature at the end of the experiment or the work backwards for the initial temperature. Okay, so in this case, we are asked for the new temperature of the water bath. So you need to be a little bit, think about this. During the reaction, heat flows out of the flask and into the bath. So my final temperature should be hotter than my initial temperature. Just make sure that you've read that carefully before you start plowing into just chugging numbers in, okay? If it had told me that the flask had cooled down, if heat had flowed from the bath into the flask, my final temperature should be colder, right? So just be careful. Okay, so we've got 5 kilograms of water, so I'm going to have to convert my mass into grams, so 5 kilograms. Use the fact that 1 kilogram is 10 to the power of 3 grams, okay? Dimensional analysis is your friend. So we end up with 5,000 grams, lovely stuff. Okay, and then my initial temperature, we're just going to leave that for a second, it's 39.2. So just leave that there. Okay, we're going to solve for delta T. During the reaction, 64.3 kilojoules of heat. So that's my Q, but I'm going to want that in not kilojoules, but joules, correct? So 1 kilojoule is 10 to the power of 3 joules. Okay, so that's 64,300 joules. All right, we're almost there. So now we're just going to rearrange and solve for my delta T because we've got the specific heat capacity, and that is in joules per gram per Kelvin. Okay, so delta T is going to be Q over M times my specific heat capacity. All right, so let's do it. Okay, so Q is 64,300 joules. My mass was 5,000 grams, and my specific heat capacity is 4.18 joules per gram per Kelvin. So what is going on with my units here? Let's just make sure everything is doing what we think it's going to do. Joules cancels out, grams cancels out. 1 over Kelvin is going to give me my delta T in terms of Kelvin. Okay, so let's get that. 64,300 even, divided by 5,000 times 4.18. My difference in Kelvin is 3.08 Kelvin. Okay, so I know that my final temperature is going to be 3.08 Kelvin hotter than my initial temperature. So what I can just do is just add that delta T to the TI to get my TF. If you like to do it the rearranging equations way, so TF on the left-hand side equals delta T. Take the minus TI to the left-hand side, it's going to be plus TI, right? Okay, so that's what we're doing essentially. So delta T then I've got as 3.08. And that is going to be the same in degrees Celsius as it is going to be in Kelvin. So I can just add it straight away. I'm not sure if ALEKs is asking you for the temperature in degrees Celsius or Kelvin. So who knows, right? I'm going to work it out in a second. 39.2. So in terms of degrees Celsius, that is 42.3 degrees Celsius. Okay. You could have calculated what the 39.2 was in Kelvin. So 39.2 plus 273.15, okay, is 312.35. Then if you add the 3.08, the final answer in Kelvin would be 315.43 Kelvin. But I've got a sneaking suspicion they're actually going to ask for your final temperature in Celsius because the initial temperature was given in Celsius. Yeah, 42.3. Okay, because nobody's thermometers that they're measuring the water bath in is going to give it to you in Kelvin. Okay, so you get the idea of that. Just be really careful. If you were asked to solve for the initial temperature, of course, hang on, let's get that to go away. Again, if you were asked to solve for the initial temperature, again, you could rearrange and solve for that because the initial temperature would be the final temperature minus delta T. Okay, so you can do it every which way.